That's what we do.
Yep.
Okay, here we go. We're recording. Last day. Oh, no, I think we're excited about it. Some of us are graduating after this, so.
Yep. Woohoo.
Okay, so just for a little bit of review. Oh, I guess I should say at the top here. Last class today. Put a sad face so it doesn't look so.
Yeah.
So just for a little bit of review, but not much because I just want to get through inverse trig and then that'll be good for us. So what did we do last day? I can't even remember. Oh yeah, we talked about coterminal. So, and moving from radians to degrees. And we talked about the graphs of trig functions. So we talked about the graphs of sine of x and cos of x. We're going to come back to those briefly, but no shifting or anything like that today. We talked about radians, right? Radians are just the distance that you've traveled on the circle, which is also an angle. Distance traveled on the circle, which is the angle. So we've already talked about the angles, we just haven't called them the angles, but now we're calling them angles. And we said that angles are often denoted by, by theta, the Greek letter theta. Okay, so that's going to come up again. So that's why I want to highlight that now. And then this isn't, well, it could come up. Two angles are coterminal. Two angles are coterminal if they have the same terminal point. If they have the same terminal point. Okay. So let's do, I'll pull in an example from last day. Just a quick example of coterminal, and then we'll move on. So let's do, let's do 37. So we've got 5 pi over 6 and 17 pi over 6. We're going to see if they're coterminal, meaning they have the same terminal point. Now, 5 pi over 6, we know what that looks like, right? And we can draw the unit circle. So 5 pi over 6, we remember that 6 pi over 6 is a full distance of pi, right? And so I'm just shy, I'm 1 over 6 pi, or pi over 6 shy of a full pi. Oh, that's a mouthful. So here, right, let's say here at this angle, we've got 5 pi over 6. Okay. And we know from pi over 6, right, that's our reference angle, we know that this point x is negative and y is positive. And so we have a terminal point, and maybe I should keep the same color just in case they're not the same. The terminal point here is negative, is it 1/2 3 over root 3 over 2? Now, I think I might have, I posted this formula sheet, the oh my goodness. I was trying to say it funny and then I screwed it up. Trig formula sheet, let's say that. Can't talk today. So if we look at this formula sheet, right, 5 pi over 6 is at negative root 3 over 2, 1/2. So negative root 3 over 2, 1/2. I had them mixed up. Wait, hey, where did it go? Now I'm going to focus on 17 pi over 6. So we know that 12 pi over 6 is a full revolution, right? And so here, actually, let's do this to indicate which color is which. So 17 pi over 6, I can rewrite as 12 pi over 6 plus 5 pi over 6. Right, and then notice that 12 pi over 6 is 1 revolution. So it doesn't actually do anything. So it's going to look like 1, oops. Sometimes it wants to show off. 17 pi over 6. Okay. But it ends at 5 pi over 6, which is the same. So these two angles have the same terminal point. Therefore, they are coterminal. It's the dog. Okay. So we'll leave that there, and we'll call that the end of the review, because now I want to get into just 6.2. There's just 2 things that I want to pull in from 6.2, and then we'll move on to 6.4, which is inverse trig. So 6.2, if we go to the notes here, is the trigonometry of right angles. So I'm going to pull this guy in here. And I'll add trigonometry of right angles. Right angles are angles with a 90-degree angle in them, or triangles with a 90-degree angle. Okay. This up here is just SOHCAHTOA, which you're probably familiar with, right? So this region here this is SOHCAHTOA. I guess I should have separated those, right? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tan is opposite over adjacent. Okay. The new stuff that we're introducing today is this lower half, but notice that they're just the flipped version of the ones above, right? So cosecant theta, so CSC is the flip of sine, right? So cosecant is CSC. I can't remember if I wrote out how to say these, so that's what I'm going to write out. But the cosecant of theta is the hypotenuse over the opposite. So these lower ones, let's call them SOHCAHTOA 2.0, right? SOHCAHTOA 2.0, right? Just kind of a little bit more information, right? So CSC of theta is the cosecant of theta. SEC of theta is the secant of theta. And these are just additional trig functions. And then the COT of theta is the cotangent of theta. Okay. So these are additional trig functions. And we're just going to use these, right? We don't need to know too much about cosecant or secant or cotangent. So we're just going to use the fact that the secant is the hypotenuse over the adjacent, for example. Uh-oh. The dog needs to go outside. Great timing. Go. All right. So we can use these additional trig functions, but we use them the exact same way that we used SOHCAHTOA, right? And so just remember that if we have, where's these notes here? If we have a triangle like this, right? Theta is our angle. And then the side that's opposite the angle is the opposite. The side that's attached to the angle, but not the hypotenuse, is the adjacent. And then of course the hypotenuse is the one that's opposite the right angle, so the 90-degree angle. It's always the longest side. So we can use these. And what I want to do is actually want to skip this the rest of the section and get right into 6.4, which is inverse trig, which is the last little bit of information that you'll need. And then we've covered everything, which is awesome. So let's see here. We will skip the rest of this section. And move on to 6.4, which is inverse trig. Okay. So 6.4 is inverse trig functions. Inverse trigonometric functions. And because I didn't put it on a fresh page, maybe I'll underline here because we didn't really do anything here. But I wanted to bring this guy in because we'll use it in 6.4. Okie dokie. Inverse trig functions. We've already talked about inverse functions, right? Inverse functions we saw way back where we said, okay, well, in order for a function, well, first off, a function to be a graph to be a function, it has to pass the vertical line test. Okay, that's fine. And then if a function has an inverse, it has to pass the horizontal line test, right? These things, especially for sine curves that we've seen, it's easiest to check them graphically. Okay, so we remember from before that a function has an inverse if it passes the horizontal line test. The horizontal line test, which will abbreviate HLT, the horizontal line test. So if we have a look at maybe the sine curve, which we saw last day, right? We graphed the sine curve last day. It starts here at the origin, and then it goes up to 1, and then it goes down to -1, right? So just go like this. So it starts here, then it goes up to 1, down to -1, and then back up again, and just kind of keeps going, and it goes and does the same thing in the negative direction. So this is sine of x. Now, the horizontal line test, it doesn't work, right? Because we're crossing multiple points. In fact, because this wave keeps going and going and going and going, it's definitely not going to pass the horizontal line test, right? So as it stands, sine of x does not pass the horizontal line test. Okay. But from your calculator, you've probably seen that there is a sign to the -1, which we read sine inverse, right? So we know that it exists. And so what we have to do is we have to restrict the domain. So what we do is we just focus on some values of x that give me a one-to-one function. So then it'll have an inverse. So what I'm looking for is, we remember that sine goes from +1 down to -1. So I need something that shows me all of those y values. Now, if I start here, so I want to stick around the origin, right? So if I start here at the origin and I move over some amount, well, this is the section that's not passing the horizontal line test. So what we actually do is we move to the left a little bit and say, well, what if I chop it off here at this bottom bit and here at this top part, right? So now what I'm going to do is I'm going to restrict the domain to -π/2 and π/2. I'm just telling you what those points are. Because now if I look at just this region, it is one-to-one because it's passing the horizontal line test. So if I restrict the domain, then I'm able to find the inverse of sine x. If we restrict the domain of sine of x to -π/2, oops, that should be a 2. -π/2, π/2, including those endpoints. Okay. We see that the restricted function is one-to-one. We see the restricted function now passes the horizontal line test and therefore is one-to-one and has an inverse. All those things kind of go together, or they do go together. So if we have sine of theta equal to some value, okay, is equal to, let's say, y from our terminal point, right? Remember the sine of the angle is the y value in the terminal point. If pxy is the terminal point, okay, then the inverse is hard to find, but it's just its own function. Then we say that sine theta, well, theta is going to be the sine inverse of y. And how we read this is the inverse sine or sine inverse of y. Okay. So then the angle is the inverse sine of the y terminal point, or the y from the terminal point. Okay. All right. So it's important that we remember that we're restricting this, the domain, right, the input for the angles to negative pi over 2. So that's, if we go back to, and we steal our, let's steal this little guy. Copy. Paste. Okay. So for sine, right, if I go negative pi over 2, I'm going down to here, right? And then if I'm going positive pi over 2, a distance of positive pi over 2, I'm going to here. So for sine, so for the inverse sine, we're restricted to these outputs. Okay. So here, restricted to these points. Oops. For sine inverse of y. Okay. Now we're going to do the same thing for cosine, but cosine's a little bit different, right? If we think about the graph of cosine, well, the graph of cosine actually starts at 1, 0, or sorry, 0, 1, and then it goes down and then it goes up. So we can do this for cos theta as well. Right? If we think about our graph here, so cos theta starts here at the top, right? And that's from last day, we know that. And then it goes down, and then it goes up, and then it goes down, and then it does the same thing on the negative x-axis as well. So this is cos. Here, the x is referring to the x-axis. Right? So cos of theta or cos x, again, it doesn't pass the horizontal line test until we restrict our domain. But if we use the same domain from negative pi over 2 to pi over 2, it still doesn't pass. We have that same problem that we saw before, right? So what we do is we restrict our domain, but we actually restrict it from 0. So from 0 to pi, okay? Because here I'm able to see all the different possible values of y, and it's 1 to 1 here. And so we restrict our cosine, our domain for cosine, we restrict it to 0 to pi instead. For the inverse of cosine of cos theta, we restrict the domain to 0 or 0 to pi instead. Okay. So instead of restricting to this side, 0 to pi is this top half. So what I'm going to do, I'm going to copy this guy again. And maybe a little bit smaller here because I want it on the same page later. So now I'm going from 0 to pi, right? So now these points for the inverse of cos or cos inverse, you have to restrict to the top half of the circle. So that can be a little bit tricky, okay, to remember, right? How did I say it up here? So if we have the cos of theta is equal to x, right? Cos of the angle is the x value on the terminal point. from the terminal point. So then what we say is, okay, well, if I move this cosine over to the right-hand side, I have the inverse cos of x. So theta must be the inverse cosine of x. So we use these inverse functions to find angles. We use the inverse trig functions to find angles, right? Theta. In a similar way, we haven't really talked about tan, but we need to know what tan looks like. So in a similar way, tan inverse, the tan of theta is restricted to, and so these points are not included, negative pi over 2 and pi over 2. So that's the same half circle as sine, but it's not including the endpoints. Okay, and we haven't looked at the graph of tan, but we can just graph it quickly in Desmos to see what it looks like. Okay, I've already got it here. Okay, I'll delete the inverse. So the tan of x is just going to be these little snakes running up and down, right? And so we've got these vertical asymptotes. So what we do to find so it still doesn't pass the horizontal line test. So what we do is we just restrict it to, and we only look at this middle one that passes through the origin. So then we restrict it to just that little section, and then tan inverse actually turns out quite nice. Tan inverse of x is this kind of long, kind of x to the power of, a third root of x style graph. Not quite, but ish, right? And so now we have these horizontal asymptotes, but remember, we can't get to pi over 2 or negative pi over 2, so that's why they're excluded. So in a similar way, tan theta is restricted to negative pi over 2. I'll clean that up. Negative pi over 2 to pi over 2, not including the endpoints. Okay. So I'll bring in this other blurb just so we don't have to write it all out. Okay. So here, right, this is a summary of what we just talked about, but what I also wanted to highlight was that inverse sine or sine inverse, we can also call arc sine, and then cos inverse or inverse cos is arc cosine, and arc tangent, of course, is the inverse of the tan. So I just wanted to highlight that we can call those pretty well by 3 different names, and they all mean the same thing, right? It's the inverse. Okay. So what we can do is, let's go here. We can use that unit circle to evaluate some of these inverse trig functions. Okay. So we can use the unit circle with the restricted inputs, with the restricted domains, depending on if it's sine or tan, or then you're on the right-hand side of the circle, or if it's cosine, then you're on the top half of the circle. So we can use the unit circle with the restricted domains to evaluate inverse trig functions. Okay. So let's just do a few of these. Okay. We'll start with 5 just because we're just starting, and then we'll do 8 just to do a hard one. Okay. But as long as you have the that unit circle, then it's not bad. The tan is a little bit harder, because so the sine is the y of the terminal point, and the cosine is the x of the terminal point. But remember, tan is y over x, and so it's a little bit harder, but I'll show you how to do it. 5a. So now I've got the inverse sine of 1, and I'm going to say is equal to theta, just because it makes it nicer to look at. So then I can rearrange this and say sine theta, right? Sine theta must be 1. If I move this inverse sine over here, and then revolving door, right? I can write it a equals b is the same as b equals a. So now I'm looking for an angle, some angle that gives me a y value of 1 in my terminal point. Okay. In the restricted domain. So I'm going to copy this here so I have it. Okay. So remember, for sine, right, I'm restricted to this half of the circle. Okay. And so now I'm looking for a y value of 1, right? That only happens once here at pi over 2, which tells me that theta must be pi over 2. There is only one angle that has a y equals 0, that has y equals 1 in the terminal point. So theta must be pi over 2. Okay. So you're going to use this this unit circle a lot, right? Let's do B. Okay. Remember, for cosine, you're restricted to this top half, right? There are 2 options where the x is 0, but you're restricted to the top half, so it is also pi over 2. Right, let's write that down. Oh man, this dog is bossy. Cos inverse of 0, and I'm going to say equals theta. I'm allowed to do that. And I think it makes it easier, so I encourage you to do it too. I'm going to bring this cosine over here and write cos theta is 0, right? So now on this restricted domain, I'm looking for an x value of 0. That only happens at pi over 2. At theta equals pi over 2. So that's your answer, right? If we want to solve cos inverse of 0 equals theta, then we found theta equals pi over 2. So what we can say, and I forgot to do it up above, so I'll go back and do that. Therefore, cos inverse of 0 equals pi over 2. And here I'll add that in. Therefore, sine inverse of 1 is pi over 2. Okay. If I have to do C, the tan inverse of root 3, okay, let's see here. C, I want the tan inverse of root 3, okay, equals theta. So what that says is that tan theta equals root 3. Okay. Remembering that tan of theta is in terms of sine and cosine, which is our x and our y coordinate, or our y and our x coordinate on our terminal point, right? Tan theta is sine theta over cos theta, which is y over x, as long as x is not equal to 0, from our terminal point. Okay. So, all right. What does that mean? Well, it means that I need to find a y value over an x value where, and a lot of these are fractions, right? So where if I cancel, I end up with root 3. This means we need to find a terminal point in the restricted domain, right? The right-hand side of the unit circle, a terminal point in the restricted domain that yields y over x is equal to root 3. Okay. A lot of the time, root 3 looks familiar, right? So you're probably going to have to use one of the points that have root 3. This one has root 3. Here we've got a root 3 as the x. So we've got two options. The other half, they're not options, right? Because one of these is negative and the other is positive. So now I'm getting negative values if I take one over the other, doesn't matter which one. So I'm limited to this half, right? Or this quarter, I guess, of the full circle, but half of the restricted domain. Okay, so my options are root 3 over 2 divided by 1/2, right? Or 1/2 divided by root 3 over 2. I'll try this one. It's going to work. Okay, so we try 1/2 root 3 over 2. Try 1/2 root 3 over 2. Then y over x is going to be root 3 over 2 divided by 1/2. Fraction over fraction, I can flip and multiply. Root 3 over 2 times 2 over 1. Those 2's cancel, and all of a sudden I have exactly what I wanted. Okay. So it worked. This point, this terminal point, is for pi over 3. So since 1/2 root 3 over 2 is the terminal point for theta equals pi over 3, we know that the tan inverse of root 3, right? Tan inverse of root 3 is equal to theta. Well, theta is pi over 3. So now we can replace this. And so it's tan inverse root 3 is theta, which is pi over 3. Good. Okay. Let's see here. Yeah. Let's do another one. Okay. We can do the last one here. In fact, I'm going to copy it over so I don't have to scroll around. And let's bring in the unit circle copy. It's going to be everywhere in these notes. Nice to have. Okay, so we do the same thing. Oh, can't erase that. That's okay. So for A, right, now I'm looking for a sign. So the y value, which is -√3/2, right? And so now here, the only time I get a negative is in this fourth quadrant here, right? For sine, I'm restricted to this region. And so I find that my angle is 5π/3, okay? But we're going to talk about that because we have to tweak it a little bit. So for A, we've got sine inverse of -√3/2 is equal to theta. Okay? So what I'm going to do is I'm going to write this as sine theta is -√3/2. In the restricted domain, right, the y value is -√3/2 over here as well at 4π/3, but that's not in the restricted domain, so I have to be on this side. So that's why I'm blocking off this side. I'm not looking at that side for sine or tan. So I see that the terminal point, 5π/3, is the point that I want, right? So theta is 5π/3. Okay. We see theta equals 5π/3. However, 5π/3 is not in the restricted domain of -π/2 to π/2. However, 5π/3 is not in the restricted domain of -π/2 to π/2. Okay. So what we do is, well, we see that these points are in the restricted domain. We just need to tweak them a little bit. So what we're going to do is we're going to rewrite 11π/6 as -π/6, right? Moving clockwise, π/6. And then here, 7π/4, I'm going to write -π/4. And 5π/3, I'm going to write -π/3. So what we do, so we rewrite 5π/3 as -π/3. And so here, I'm going to copy this again here, make it nice and big this time because I'm going to draw on it. Oops. Thinking about the cosine, right? I'm not going to need to make this change for cosine, right? Cosine just preserves the values that we have. So it's for sine and for tan. That's when we need to change these points, right? Change them from 11π/6 to, well, the first one, let's see here. Here, this is -π/3. Okay. If you have a look, right, if I go the same distance in the positive side, right, the furthest one away from the x-axis is π/3. So now I'm just going a negative direction, -π/3. So what we can do is we can change this 5π/3 to say -π/3. Okay. Same idea here. this distance, instead of 7 pi over 4, you're going to change that to negative pi over 4. Same here. Instead of 11 pi over 6, do negative pi over 6, right? Just moving in the negative direction. Okay. So now we see that the sine inverse of negative root 3 over 2 is negative pi over 3. So therefore, the sine inverse of negative root 3 over 2 is negative pi over 3. Let's do the same thing for B. B is the cos inverse of negative 1/2. Oops, I think, let's see here. Yep. So now I need an x value, but remember cos is restricted to this top half, right? And so now I need an x value that's negative 1/2. That only happens once in the restricted domain. It happens twice on the circle, but once in the restricted domain. So we're stuck here at 2 pi over 3, right? So now I can just start saying, okay, well, that's going to be 2 pi over 3 from the unit circle. 2 pi over 3 from the unit circle. Okay. How about C? So now I have the tan inverse of negative root 3. This is a similar problem that we just solved, right? So let's have a look. I want the tan inverse of negative root 3 is equal to theta. So again, I'm going to do a little bit of work here and say negative root 3. Actually, I've been doing them the opposite. Tan of theta is the negative root 3. So again, we need to find a point with xy coordinates that simplify y over x to be negative root 3. That negative can come from either the y or the x, right? In this case, because we're talking about tan, we're restricted to this half, so it's going to come from the y, right? So again, we need to figure out, okay, how am I going to get just a root 3? And so you can try negative 1/2 over root 3 over 2, but negative 1/2 over root 3 over 2 puts me at 1 over root 3, negative 1 over root 3. That's not good. So again, I'm going to use this point here. So if I let theta be negative pi over 3, we try I think 1/2 negative root 3 over 2, then y over x, oops, put that down here. Then y over x is going to be negative root 3 over 2 divided by 1/2, which is negative root 3 over 2 times 2 over 1, which is going to cancel. So now I'm at negative root 3. So now we've solved that, and we can say tan inverse of negative root 3. Therefore, the tan inverse of negative root 3 is equal to, and we grabbed those coordinates from this point here, and we've rewritten it as negative pi over 3 equals negative pi over 3. Good. Okay. So The last thing we're going to do is going to take this just a little bit further. And it's pretty fun because it looks hard, but it actually isn't hard once you see a few of them. So we'll get kind of familiar here. We can start with this question first. Question. Okay. So if we have a triangle, some right triangle here, then if I have theta up in this corner, then what we're saying is that the sine inverse of some value is equal to the theta. But sine, remember, is opposite over hypotenuse. So sine inverse of 8/10 is equal to theta. Right? So you can just put those values in here, 8/10. The cosine of theta is adjacent over hypotenuse, 6/10. So those are the values that are going to give me theta. Tan, opposite over adjacent, 8/6. Not bad. How about the next example? Yeah. What if we have to find something really hard looking like this? Okay. What we're going to do is we're going to boil this down into let cos inverse of 5/13 be theta. Okay. Then we're going to use that theta to figure out what our triangle looks like. Okay. And then essentially I need to find sine theta, but I already have the triangle, so then I'll be able to find all these values. Okay, so I'm going to follow these steps because it walks you through the problem, but I'm going to write them out here so we have them. So here, let's see here. Let theta be the cos inverse of 5/13. Doing that same thing that we did earlier, where we switch, so we move the cosine inverse over, so then we're at cos theta is 5/13. Well, if I'm taking the cosine of theta, well, the answer is adjacent over hypotenuse, right? And so if I have this theta here, I know the adjacent is 5 and the hypotenuse is 13. Okay, so here, which is the adjacent over the hypotenuse. Okay, so then we can fill this in and we can say, well, the adjacent is this side and the hypotenuse is this side. Now, I need to use the Pythagorean theorem to solve for the remaining side. Now use the Pythagorean theorem to solve for the remaining side. To solve for the remaining side. Right? A squared plus B squared equals C squared. As long as you're letting C be the hypotenuse, it doesn't actually matter which one's the opposite and which one's the adjacent. C has to be the hypotenuse. Okay. I'm going to let A be the one I'm solving for, only because when I write my B's, they look like 6, and that can get confusing. Okay, so here, I'm going to say that this A equals, right, even my A's don't look very good. So, oops, here, A squared plus 5 squared equals 13 squared. Okay. 13 squared is 169. So a squared plus 25, 5 squared, I know 169 minus 25 is 144. So a squared is 144. Remember when you take the square root, you have to actually have the positive and the negative value. So a is the plus minus root 144. However, there are no negative distances, right? So actually, I'll do it in pink because it's kind of important. We can't have a negative distance so we only consider the positive. So then we found that a must be 12. Right, the root of 144. So now we can say a is 12, right? Or that side is 12. Okay. Now I go back and I say, okay, well, I let theta be this whole thing. So in sine of that whole thing, sine of theta, from theta, I just need the opposite over hypotenuse, 12 over 13. And we're done. Hey, Bissy. She's so bossy. She's so bossy. Since we let theta be the cos inverse of 5 over 13, we can rewrite sine of the cosine inverse of 5 over 13 is just the sine of theta. Well, the sine of theta from our triangle is the opposite over the hypotenuse, 12 over 13, which is 12 over 13 from our triangle. Hey, not bad, right? As long as you remember to switch this and make that cosine and then to solve for your triangle, but as long as you follow those steps, it's actually pretty fun. Right? So let's just do a few more of these. Oh, it's just a blank page. We'll do 2 of these, and then we'll be done all the material for the course. So that's exciting. All right. So let's do, it doesn't matter which one we do, 29 and 31, how about? I'm picking 31 because it's got the secant, right? Could have used cosecant or cotangent. Just remember that you have those from the very beginning in 6.2. Where was it? You have those cosecant is the hypotenuse over opposite, secant is the hypotenuse over adjacent, and the cotangent is the adjacent over opposite. So just have those available. And then these problems won't be a problem at all. So 29, if we want to solve cos of the sine inverse of 5, or 4 over 5 rather. First thing we're going to do is we're going to let theta be sine inverse of 4 over 5. That's the key step. Then sine theta must be 4 over 5. So from here, I can set up my triangle. I just draw any right triangle here. Usually I let this guy be theta, doesn't matter. So the sine of theta, opposite over hypotenuse. So 4 and 5. And here I'm going to say A equals, right? So now I have to solve for that A squared plus 4 squared equals 5 squared. So A squared is 25 minus 16 is 9. So A must be 3. Okay. So now I have the full triangle, and I've also swapped this whole mess out for theta. So the cosine of theta is the adjacent over the hypotenuse, 3 over 5. So cos of the sine inverse of 4 over 5 is essentially the cos of theta, right? Because we swapped this out for theta. So now the cos of theta is the adjacent over the hypotenuse, 3 over 5. Okay. Let's do 31, just so we have it. Last question of the term. Weird. Oops. So 31, we've got the secant of sine inverse of 12 over 13. Secant of sine inverse of 12 over 13. So again, I'm going to let theta be sine inverse of 12 over 13 to figure out what my triangle looks like, and then I can do the secant. So maybe I'll put this on a fresh page there. If I let theta be sine inverse of 12 over 13, then the sine of theta is 12 over 13. I can make my triangle. Let that be theta. Sine theta is 12 over 13, so the opposite over hypotenuse. And then I'm trying to solve for, let's call this side A equals, so I've got A squared plus 12 squared equals 13 squared. 13 squared is 169 minus 12 squared is, so A squared is 25. So A must be 5. And now from that SOHCAHTOA 2.0 that I gave you at the beginning, whoa. Let's copy this in 6.2. So it's from your 6.2 handout. I'll delete all of this there, right? So now I want the secant of theta, right? The secant of theta is this one here, hypotenuse over adjacent. The hypotenuse is 13 and the adjacent is 5. So what we know then is the secant of the sine inverse, may as well write it all out, sine inverse of 12 over 13 is the secant of theta, which is the hypotenuse over adjacent, 13 over 5. Here, Done. And because I have it, how about, oh, hey, wasn't it coming in? Great job. It's the end of the material. That is the end of the term. Any questions?
Just one thing. Did you already post the form sheet?
Did you say formula sheet?
Yes.
I did. I posted. Let me go to Moodle here. I posted. Let me make sure I'm in the right course. I am. I posted the 2 formula sheets that I showed you last day, the Math 120 formula sheet, which is the one that you would usually have, but then also the trigonometry formula sheet, which I find more useful. It's the one that has that fancy unit circle that we were using today. Just, we didn't talk about the laws of sines and cosines, so just ignore that on there, but that's okay. So
Thank
those might be nice to have handy somewhere.
Yep.
Awesome. All right. I'm going to stop the recording, but let me know if you have any questions. Otherwise, thanks for coming to class.
And
You too.
Emily, for next week, like, do we have any classes or review classes there?
No, so no review classes, but what I'll do is I'll send out an email once I've decided a good time I'll have office hours, but just designated for this class. So, and then I'll have a couple of practice problems you can work on, but I'll also post a practice final.
Everything will be on WebAssign, right?
Yeah. And you'll have to submit your work to me, right? Just like we've been doing, but your work is worth 50% of the final exam grade.
15%, right?
50, half of it.
Oh, 50. Okay. Of the final exam, right? Okay.
So you want to make sure, but that's mostly because even if you get the question wrong, if you've done it kind of in a good way, then I can give you more marks, right? So make sure that you write everything down and just have all your work organized.
Okay, I'll try that.
Okay.
And what's the weightage of the final exam towards the course grade?
It is, where is our, I can't quite remember, so let me just, the final exam is only 20% of your grade.
All right. And are there any assignments for this week?
I think I posted some. I'll post one for 6.2 and 6.4 as well.
There
But
are 4 you, I think so, by tomorrow.
Okay, yeah, so there's some posted already, and I think I made them due for Friday, but then the ones for 6.2 and 6.4, I'll make them due next Friday.
All right. Thank you.
Awesome. Stop
Thanks,
this.
Evelyn.
Thank you.
Thank you for helping.